And I guess no one's coming from the undergraduate campus of WashU time. We're actually going to start at 10:15 if we can. So welcome to the first lecture of our mini course in biostatistics. I'm going to give you a quick rundown of what I'm hoping everyone will get out of the course, what we're expecting you to do, and importantly what we're not expecting from you. So the goal of this course is to get you guys thinking about data and the numbers that you generate as in the course of being a scientist, and how to think carefully about these numbers, what they mean, what they're telling you, what they're not telling you. So that's goal one, just thinking carefully and thoughtfully about the numbers that you generate. Goal two of this course is to understand some basic programming tools for reading numbers, writing numbers, and transforming numbers. I really hate to see people spending 2 days in Excel doing some repetitive task, for 6 hours a day. I would much rather, after this course, you guys have the sense, okay, I'm going to spend 2 days teaching myself how to automate this. Maybe you didn't win any time the first go around, but the next time you have to do the same task, it'll be a win. So that's the two goals: basic programming for dealing with numbers and basic statistical concepts for thinking about numbers. And so this is a short course, obviously. We're not aiming for expertise or mastery. I just want to get you to a point where you feel comfortable with some of the basic concepts, comfortable enough to start teaching yourselves or asking other people who have more experience how to do this in a computer or what sort of statistical approach is right, just to know the basic vocabulary so you can go from here. So that's what we're really hoping for. One thing that I want to explicitly point out that I'm not aiming to teach is any kind of paint-by-numbers statistical formulae. Because I don't want you to get the idea that statistics is some sort of magic dust that you sprinkle on your data at the end of the science when you have to satisfy reviewers. That's not what statistics is. Statistics is how you design your experiment in the first place so that it'll generate numbers that you can actually interpret. Statistics is how you convince yourself that the numbers are real. To digress a little bit into almost philosophy of science. Science is a tricky thing. You have to be your hypothesis's biggest supporter. No one else at the very beginning is going to believe the hypothesis except you. It's you out there alone trying to coax the data to tell you what you think is out there. And so you need to be the supporter of your data. The assay doesn't work so well, and the numbers are noisy, but you think there's something in there. You need to believe in order to continue doing the science. But at the same time, you have to be your data's biggest critic, because data can be deceptive. And if there's not something in the data, if it was just a random fluctuation, you had better be the one to find that out. You don't want someone else to tell you that you imagined the biology. That's really embarrassing. So you have to be critical of your data. And I mean, this is really difficult. We humans are pattern matching machines. It's easy to think that we see something. And this makes sense. If you're a hunter out in the forest, it's a really good idea to be able to see just the faintest shadow of the lion in the jungle behind you. And if 9 times out of 10 you jump and there's no lion, it's still worth it for that 1 time out of 10 when you did see the lion and you get to go home and maybe have some kids of your own one day. So we're built to see patterns, and this is what lets us do science. It's what lets us see the lion in the jungle, but it's also what lets us see the lion in the clouds. And this might be good for the poets, but it's not good for the scientists. So how can we as scientists tell if we're seeing a lion in the jungle or seeing a lion in the clouds? And statistics is our tool for that. Statistics is how you can convince yourself that you are not wrong. Statistics isn't about convincing the rest of the world that you're right. Statistics is what you do as you're going through your scientific process to make yourself believe in your data, that these are real, that I can go forward with this. Most of the statistics that you do shouldn't wind up in your paper. Most of it should be what you're doing as a day-to-day process of being a scientist. Okay, Okay, so enough with the harangue. Let's talk about what we're expecting from the course. This is a course that does not expect a statistics or programming background. So I'd like to take a quick poll. Who has had a full course in probability or statistics before? Just raise your hand. Okay, now keep your hand up if that full course was taught by a statistics department. Okay. Let's do the same thing for programming. Who has had a full course in computer programming? And was it from a computer programming, from a computer science department? Okay. So that's good. This is perfect. So you've got some people who know some statistics, some people who know some programming. If you know the programming, be prepared to help out your neighbors. During the programming sections of this course, there's going to be interactive exercises with time to work on your own on your laptop. So if you know what you're doing, help out people who don't. If you know a bit about statistics, this class is going to seem a little strange. The pacing is going to be a bit weird. We're going to teach some really basic concepts in statistics in a very different way than often gets taught, in a way that really fundamentally is driven by the ability of computers to do things that you couldn't do easily by hand. So don't get frustrated by the pacing, because we will get there. All right, so just one quick note about the mechanics of the course. The course is 8 lectures. They're going to alternate weekly between a statistics topic and a computer programming topic. And we're doing our best to make these topics kind of mirror each other, or at least rhyme a little bit. And there will be weekly homeworks. So these homeworks are going to take the form of IPython notebooks that you download from the course Blackboard page, fill in, and upload back to the course Blackboard page for grading. The homeworks are going to be due before class the next week. So you have 1 week to work on the homeworks. You can submit late for a 30% penalty. There's not a quiz, no quizzes, no tests, no projects. So it's really doing the homeworks to get your 1 credit. And remember guys, you're graduate students, the goal here isn't to get A pluses and everything. The goal is to learn something. And so take the homeworks as an opportunity to learn. In particular, we've got help sessions on Thursdays. So that seems like a good time. You've had a little bit of chance to download the homework, look at it, decide if you want to go talk to someone about how do I actually get this working. There's also the help forum on the Blackboard course discussion page. I've made it so that you can post anonymously if you feel like it's a silly question. First off, there aren't silly questions, especially with computer programming. But if you're worried, feel free to post anonymously. Also, this is the first time that we're teaching this course. So feedback in any form, from an anonymous post on the course Blackboard to email to me, any kind of feedback will be really valuable for properly pitching this course and making sure that you guys get the most out of it. So if it's going too slowly or going too fast, please let us know. This course is for you, so tell us. All right. So. Oh, right. So I sent this email out. Who got the email that I sent out? First off, I figured out how to not make the email look like it came from an old person who doesn't know how to work the course web page. I've now figured that out, so I won't send you weirdly formatted other emails in the future. But hopefully, formatting aside, you did in fact read it, and remember that I asked you to calculate your height in centimeters. Does everyone have their height in centimeters? If not, get your phone out and figure out how many centimeters tall you are. So we're going to build a data set to work with in class a little bit. So first off, what's the simplest way to have a bunch of numbers? How should I represent a bunch of numbers? Anyone? Shout out something. Table. Write it down. That's the dumbest thing we could do. So we always start with the dumbest thing we can do, and we'll work up from there. Okay, so I don't want any decimal places. Just read out, just start shouting out heights. I'm not even going to look. I'm just going to start writing down numbers. So
172.
172.
180.
180.
183.
162.
175.
183. 183.
162.
163.
180.
160.
165.
164.
167.
181.
163.
163? Was that, what did I just do the last one?
Yeah.
163, thank you.
172.
What was that?
72. 172.
160? Any others?
170.
170, all right. I think that'll be a good number, unless anyone is upset that I didn't get that right.
188.
All right.
155. 55.
155?
Yeah.
Okay, good. So, this is a table of numbers. Now, we can see already, looking for the numbers, that, that there's something going on with the numbers, but it'll be a lot easier to get a sense of the structure of the numbers by plotting them out. So we're going to make the very simplest possible graph, and that is known as a dot plot. So we're just going to put a dot on a number line everywhere that one of our numbers belongs. And I mean, I know this is obvious, right? But the point is, anytime you get some data, the first thing you should do is just look at it. Figure out a couple different ways of looking at it. Looking at your data is the best thing you can do statistically. The worst thing you could do is start churning numbers and calculating things. Just look at what your data are. That's the, that'll be your best summary statistic. All right. So we got 150. Let's make it longer. It doesn't have to be perfectly straight. Doesn't divide evenly. Let's 140. That's better. Don't tell me the spacing is uneven. Okay, so now we're just going to go through the data and put numbers, put a little dot, sort of approximately where we see. Okay, so we've got 172, 180. You just want to shout out at me? Let's just go down the list, starting in the left column. Okay, what do we have? We've got one more 180, then what?
183.
183.
162.
162.
175.
Yeah, unison.
183.
193.
83.
Oh, did I get it wrong?
Yeah. 183 instead.
Oh, all right, fine. Okay.
183 again. 162.
163.
Yeah.
188.
88.
180.
Were these 180?
Yeah.
160.
160.
165. 164. 167.
Oh, there's an emergent leader. I like that. Good work.
181. 160. 163. 173. 172. 178. 155.
Okay. So we can see some things. this, we can start to form some hypotheses. Maybe, are there two groups in these numbers, maybe? I wonder what biology might be driving the two groupings that we're seeing. And we see some outliers. Good to have outliers. What, is this unusual? Is it like totally mind-blowing to have an outlier here and here, or is it like basically what I would expect with a class of this size? This is the sort of questions that we're going to be figuring out how to answer in the course. But this took a little while to make and to draw out. And sometimes you want to summarize your data. So the best thing to do is just to look at your data, graph it out. But if you have a whole bunch of data, the dot plot's going to get pretty busy. We might need some simple summaries. So the first thing that we're going to talk about for this course is summarizing numbers. How do we concisely summarize what's in this table, what's in this dot plot? So let's start by being very concise. Let's say that I want one number to tell you everything that there is to know, or at least as much as one number can tell you about this data. Should this number be here? Is that useful? Not really. Here is not useful. Here seems, kind of useful. But maybe we can be a little more formal. This is bad, better, bad. What do we mean by bad and good? What do we actually mean when we say that a number is a good summary or a bad summary of our data? So I'm just going to keep this up here for later. So fundamentally, for our summary, we want a number that is not too far away from all the other numbers. It's somehow close. So I'm going to write this out formally, and it's going to be scary math. And then we're going to go through all the pieces, and it won't be scary math anymore. So we want R min sigma I. Okay. What? All right, so let's take this apart piece by piece. First off, I'm going to assert that there's some function that measures the distance between 2 points. So we'll call this distance between point A and point B. And the particular points that we're interested in are S equals the summary. So that's, this black arrow. Where do we move that black arrow? Where should the summary be? So let's call this is S. And then these are our data. Each one of these points is a data point. This is the first data point, second data point, the third, the fourth. We can number our data points. So you probably remember from your math classes that when you have a bunch of things, you've got data, and it's a list of numbers, 1, 5, 7, 9, what have you. Data, and a little underscore 0 will be the first element of our data list. Data 1 will be this list. Okay, but it's actually being a little weird. Why are you counting from 0? That's what computer scientists do. You'll have to learn that for the programming course. So 0 is the first element, 1 is the second element. Trust me, it makes everything way easier. But this is just notation. So we've got a distance function to measure how far our summary statistic is from any given data point. So that's this DI, the ith data point. And then this, do you remember this from math class? The sigma, the summation notation. So that's just for every data point, we're going to measure the distance between that data point and our summary and add them together. Everyone feel okay with that? Okay, so what's R min S? So we want to find the S that minimizes this sum. So that's what, so we don't care what the minimum sum is. That would be if we just say minimize over this sum. Argmin means tell me the S, give me the argument, which is S, that gives us the smallest sum. Okay, so this is our formal math. That's into the formal math portion of the course, or at least today. So again, we can write this whole thing out as data 0 plus distance and so forth. Okay, so that's all that summation is, and we want to find the best S. Okay, so we've got that. So what is the last piece of the puzzle that we need to define before we can actually start figuring out what a good summary is going to be? What have I not yet defined?
Distance?
Distance. What do we mean, distance? All right, what's the simplest possible, what's the stupidest possible thing we could say to mean distance? Did I hear difference? Yeah. So, we could say, okay, the distance between S and D equals, S minus D. And we want this to be as small as possible. Okay, this is actually not going to work very well. Does anyone see why that's not going to work very well?
Negative numbers.
Negative numbers. We could make our S like hugely negative, and this distance is going to be tiny. And we can make it even more hugely negative, and absolute value. All right, this is a very simple notion of distance. Oh, bad board work, Zach. I'm going to have to hide one of these so I don't have to erase our data set. Everyone feel comfortable with this? We're going to draw out a number line with a simpler toy data set and figure out what S is that minimizes that sum of absolute distances. Okay, so let's draw a simple number line. Okay, we're going to have a data set that's a little weird. So 1, 1, 2, 4, 32. No one has ever gotten data like that out of one of their experiments, right? Like, never happens that you have some weird number and you don't know what to do with it. But that is what we have. So let's draw out a number line, a highly approximate number line. I'm not even going to put tick marks on it. It's going to be that approximate. So we've got 1, 2 1s, a 2, a 4, and a 32. Okay, and remember, we want to minimize Okay, so let's just start somewhere. Let's say we're starting here. That is our test value for S. Okay, so we've got this distance, this distance, this distance, and 2 of this distance. Can we make this sum smaller if we move S in one direction or another? Like, what if we move S 1 unit here? What just happened? Right, this one got smaller, so we got 1 smaller over here, and we got 4 bigger over here. So we made the sum go up by 3. That wasn't very good minimizing, was it? Okay, so if we move S 1 unit over this way, obviously we're going to go down by 3. So that's good. Now it's over here. We can keep moving S all the way until we get it to this point, and every time it's going to go down by 3. Does everyone believe me? Right, so now we've got S here. What happens when we move it one more point to the left?
It was 2.
Down by 2, because we're going to go up 1 for each of these data points and down 1 for each of these, so we're still going to keep moving it left. So where are we going to wind up? 2. Yeah, S is going to be in balance over here. So first off, we accidentally did calculus. We solved the problem by looking at the derivatives of a function. But secondly, what have we derived? Does anyone know what this number, this middlemost number is called?
The mean?
Median. Okay, so starting from a fairly natural definition of distance, we actually derive a pretty decent summary of our data, which is called the median. But, and you know, this is at some kind of balance, but it's a little bit of a weird balance. Like if you imagine this was a teeter-totter, you know, if I put my finger here, would this line be in balance? No, it would flop over. So how do we get a teeter-totter in balance? Because maybe that leads us to a different notion of how we should measure distances. So a teeter-totter will get into balance when the sum of the distances above is the same as the sum of the distances below. So that says, right, so a teeter-totter will be in balance when so here we actually do use the sign to distances. We want the negative distances to equal the positive distances. That gives us teeter-totter balance. So what number? How do we calculate that?
Add up all the points and divide by the number of points.
Yeah, so where do you, how does that come from this formula? Let's think about it. So let's just expand this a little bit. And I promise this isn't just math line grade. I really do promise this will yield insight, which is my goal. So let's say, you know, we've got some number of data points. So we've got, you know, let's expand the summation. We've got S minus data 0 plus S minus data 1 plus S minus data 2. Let's just do 3 data points. That equals 0. Okay. We don't need these parentheses, right? They're not actually helping anymore. So we can take all the parentheses away, and let's just move the data points over to the other side because they're negative. So let's get S plus S equals D0 plus D1 plus D2. Okay, so solve for S. Everyone see this? This is 3S. 3 times S equals this, so we'll just divide these by 3. And we got teeter-totter balance. So this number should look familiar too, right? It's the mean. But what is it, what distance is the mean minimizing? Because obviously it's not this absolute values thing. We're going to accidentally do a little more calculus, unfortunately. It turns out that, remember how we did the median? We just kept moving S until it didn't go positive or negative? And that was like looking at the derivative. And we say, well, when the derivative is 0, we're at the minimum. So here we're saying when this sum is 0, we're at the minimum. So this sum has to be the derivative. Does everyone sort of vaguely follow? So what function is that the derivative of? Integrate, oh god. Fortunately, we don't even care about constants. We just want to know what the minimum is. And so the integral of this is going to look something like squared, right? Does everyone believe me that if we take the derivative of this, it's going to basically look like that, except for some constants that are going to go away because, zeros on the other side? Okay, so that's telling us something really important, something really fundamental about the mean. That the mean is trying to minimize the squared distance. So let's actually work through some of these calculations with the mean. Okay, so this is 1, 2, 4, and 32. All right, so again, let's do the same thing. We're going to just sort of take a guess as to where to start. Let's start at 10. All right, so what is our sum of square differences if we start at 10? Well, this is 22, right? So we 22 squared plus, what's this distance? 6. 6 squared, what else should I add? 8 squared, 9. Yep, 2 9s. Okay, I already got calculated this out in advance because, boy, this is 746. Okay, what if we step to 9? So this one's going to go up 1, and these are all going to go down 1. So that's 23 squared plus 5 squared plus 7 squared plus 8 squared plus 8 squared. Right, that's 731. Okay, so it went down. That was good. We're going in the right direction. Go one more. All right, let's go to 8. Okay, I'll just assert that 8 is 722. And how about 7? We could all punch this into our calculator. And I will further assert that 7 gives us 731. So we hit the minimum and then picked back up again. So 7 is the point that minimizes these square distances. 7 is, of course, also the mean as you would calculate it. And note how different 7 is from 2. These are really different summaries for this set of data. Why are these summaries different? Why does minimizing the absolute differences give us a number that's here, and minimizing the squared differences give us a number that's here? Anyone? What happens when you square a biggish number? It gets much bigger. So based on how the mean is defined, it really cares about big distances. And so if you're going to summarize your data with the mean, that means that you care about big distances. Should you care about big distances? It depends. Should you use the median? It depends. You need to look at your data and decide, is my data dominated by big distances? Is my data really mostly clustered around one thing with one crazy outlier that I'm certain is instrument error because I know that Joe Bob just used that machine the day before and he never cleans it off, right? A lot of statistics is taste, is understanding your data, is having a sense of what your data look like and how to summarize it in a way that is fair to the data. So, which one is better? There's no real answer. They're both useful in different ways. Now, I should mention that, we talked about how the mean is sort of teeter-totter balance. The mean is also the position where if you can imagine if we had a little peg here that could slide, right? And we put a rubber band to 32 and 4 different rubber bands over to here. Where would this sliding peg wind up? It would wind up at the mean. So that's a sort of very natural measurement of where the middle is. And why is that? Well, the spring constant, the energy in a spring is proportional to the squared distance. So there's a reason. There's really fundamental physical reasons why we should be interested in squared distance. There's also good fundamental physical reasons why we should be interested in absolute differences. But what we see is basically the mean penalizes outliers because the squared gets bigger faster than just the absolute value. There's one other way we can summarize the data. One other sort of weird seeming distance function. So remember, the median penalizes outliers less. What if we decided to penalize outliers not at all? How do we write a distance function that doesn't penalize outliers at all? Let's just start. Let's say, okay, distance between S and D equals 0 if S equals D. So if we're sitting right on top, the distance is 0. That seems like a pretty important property for a distance mass. And then we're just going to say, if we're not sitting on top, it's just going to be a constant penalty. So this doesn't penalize outliers. It could be, this is the distance metric version of close only counts and horseshoes and hand grenades. We don't care about close. 0 and 1, binary. This is good computer science distance. So what does that give us for this particular data set? All right, so let's try, let's just try a number. What's here? What's the distance according to this metric? What's the sum of the distances from this point to all these other points? So remember, we're going to do a summation, sigma. The distance between S and DI, and we're going to add that up. So what's the distance from this point to this point? 1 here. What's the distance from this point to this point? Okay, so when we add up all the distances, what do we get? 5. Okay. So I think you can probably see that no matter where we choose, if it's not sitting right on top of one of them, it's going to be 5. All right, so what if it is sitting right on top of one of them? What's the distance here? 4. All right, so this one's 4. This one's 4. This one's 4. What's this one? 3. So, what is our minimum position? Minimizes this distance function. 1. Okay. What is that? Does anyone know the name for that? Mode. All right. So now we've got the mean. 7 or 8? 8. Okay. Thank you. We've got the median. And we've got the mode. And you've heard about these since high school, I'm sure, right? Like this is not groundbreaking. But what I've tried to do here is to give you some intuition for why these numbers work the way they do. Why is it that the mean gets pulled around by the outliers? Why is it that the mode always sits on top? Fundamentally, it's how we define our measure of distance. How different are two things? And statistics is all about measuring how different are two things. So this is the simplest possible introduction to conceptually how do we measure differences between numbers and groups of numbers, and why does that give us different results? And this is going to be a theme that comes up. How do we measure a difference? And is this measurement of difference appropriate for my particular data set? Now, of course, since this point is the mode, what would a bimodal data set be? Just as a sort of point.
Two values.
Two values. So fundamentally, a data set like this could only be bimodal if there were exactly two peaks with exactly the same number of points right on top of each other. Sort of colloquially, we refer to data as bimodal if there's sort of two biggish peaks separated from one another. They don't always have to be the exact same height. And we could actually relax this definition of distance to allow for that. We could say, okay, the distance is 0 if S is close to D. So we could allow sort of, that this would be one mode. These would all count as part of that mode. So we're going to be thinking about our data and whether it's bimodal, whether the mode is a useful summary, whether the mean or the median is a useful summary. So these are three different summaries of our data. And so I've been calling these summaries S for summary. S also is for statistic. So these are three classic statistics. A statistic is any single number that measures some property of a group of numbers. So you've seen the mean, the median, and the mode, and now we understand why they work the way they do. These three different statistics are all measures of what's called central tendency. They measure where the data is. It's a question of location. Are our data points here, or are they here? So, what's the next question you ask after where is something? You walk into the doctor's office and he says, you have a tumor. The first thing I'm going to ask is, well, where's the tumor? What's the second question you ask about the tumor?
How big is it?
How big is it? Yeah. Can you cut it out? How much are you going to have to cut out? So we have now talked about questions of location. The next section of the class, we're going to talk about questions of scale. How big is it? But first, we're going to take a short break.